Okay, 2.7, derivatives and rates of change, and now we're talking about velocities. In general, suppose that an object moves along a straight line, as in the example of the falling ball, right? You drop a ball from the top of a building. Okay, so that kind of thing. So suppose an object moves along a straight line according to an equation of motion s equals f of t, where s is the displacement or directed distance of the object from the origin at time t. So sometimes we say it's a distance function. Sometimes we say it's a position function. Okay. It moves from one position to another. So where is its position as time elapses? So in the time interval from t1, which is say a number a, to t2, which is a plus h, the change in position is the difference in the evaluations of the function, the position function, for those two inputs. The average velocity over this time is this same displacement, right? That's the same thing we were just talking about, the change in position over time, because it's distance divided by time, right? So a velocity, which is a rate is a distance divided by a time, right? That's equivalent to the old d equals rt. But instead of distance now, we're going to be using s a lot for the change in position. S is the position at time t. So average velocity is f of a plus h minus f of a all over h. Sounds familiar, which is the same as the slope of the secant line, PQ, in figure 6. Okay, so this is a version of y2 minus y1 over x2 minus x1, except we made a substitution. We threw that variable h in there, and so it doesn't look exactly like that. But slope of the secant line, slope of line, the blue line. Now, of course, we're going to try to approach the pink line. Now suppose we compute the average velocities over shorter and shorter time intervals, a through h. So this interval here is getting shorter and shorter and shorter and shorter, and we're going to try to get a velocity rate of change at an instant, at the instant a. We let h approach 0, so we let this distance here go to 0. As in the example of the falling ball, we define the velocity or instantaneous velocity. Well, those aren't the same thing. But if we're talking about the limit, then we're talking about the instantaneous velocity, the velocity at an instant, at time t equals a to be the limit of these average velocities. Okay, so the limits of the slopes of the blue lines that we get as we let h go to 0. Okay, so velocity at time a is the limit as h goes to 0 of the difference quotient, f of a plus h minus f of a all over h. This means that the velocity at time t equals a is equal to the slope of the tangent line at p, the slope of the pink line. Example, suppose that a ball is dropped from the upper observation deck of the CN Tower 450 meters above the ground. We talked about this example. I believe this tower is in Toronto. So here are our two problems. What is the velocity of the ball? Okay, the rate of change of the position of the ball, the velocity of the ball after 5 seconds. Secondly, what's the velocity of the ball when it hits the ground? How fast is the ball traveling when it hits the ground? We will need to find two different velocities, both when t equals 5 and the velocity when the ball hits the ground. So let's just get a general velocity. It's efficient to start by finding the velocity at a general time t that we can apply when t is 5 and when t is however long it takes for the ball to hit the ground. Okay, so let's get this general velocity. We have a position function, right? We got a position function, and we're going to get the velocity. The velocity is the rate of change at an instant of the position function. In other words, the derivative of position function, which is f of t, a function of time, 4.9 t squared. And so that's our f. And so now we're going to get f of t plus h, which now the input here is t plus h instead of t, which is the thing that gets squared, the result to be multiplied by 4.9. That is what the position function does with its inputs. Squares the input, multiplies the result by 4.9. The first input is t plus h, then the input is just t, so there's f of t right there. And now we are building an expression. We're going to take a limit and get a velocity that way. And we can do some algebra and say, okay, well, let's get the square of t plus h, which is t squared plus 2th plus h squared. We are factoring 4.9 out of both of the terms. So we could say, you know, in the top here, that what we have is 4.9 times the difference of the two things, the first of which is the square of t plus h, and the second of which is the square of t. And then simplify the part inside the big parentheses. And so we'll expand the square of t plus h the way we said, and then there's also that minus t squared. Well, you can see the canceling that's going to happen. And h is going to be a factor of each of the terms in the numerator. So you can see how we're going to get a simple expression, and we're going to be able to take that limit as h goes to 0 to get an expression for the velocity. So factor out h, cancel, let h go to 0. That's going to take that thing and let it go to 0. And so then h will be completely out of the expression, and we will be multiplying the 4.9 by the 2t and getting 9.8t. That is the velocity at time t, which is the derivative of the position function. So now, since part A is asking what is the velocity of the ball after 5 seconds, we can just say, well, the 5, that's the t, so we're going to take that 5, throw it right in there for t, do the multiplication, and we're going to get 49. So the velocity is 49, and we've got the units there. Okay, velocity is, in this case, in meters per second, not miles per hour. Okay, that'd be a kind of units you'd have for velocity, but in this case it's meters per second. So that's going to be our answer for part A, 49 meters per second. Part B, how fast is the ball traveling when it hits the ground? Okay, so now we've got a velocity function, and now we've got this question, how fast is the ball traveling when it hits the ground? Well, we could use our velocity function, which is 9.8t, if we had a t. But in part B, we don't have a t because we don't even know how long it's going to take the ball to hit the ground. And so that's the first thing we're going to have to figure out. Since the observation deck is 450 meters above the ground, the ball will hit the ground at time t when s of t equals 450, right? You're 450 meters above the ground. You have to fall that whole 450 meters for the object to be on the ground. And so we're going to set the position function equal to 450 and solve for t to figure out how long it takes the ball to hit the ground. When we know how long it takes the ball to hit the ground, we can use the velocity function to get the velocity at that time. Well, we're solving this little quadratic equation here to do that. And so dividing both sides by 4.9, divide both sides by 4.9, we're going to have a number, and we're going to take the square root of both sides. Square root of both sides. Of course, when you take the square root of both sides, one side is plus or minus, but we don't have the minus here because we're not talking about a negative amount of time. So we're only taking the positive square root of this 450 divided by 4.9. That is the square root of a number which is a little bit less than 100. And so the number itself is approximately a little bit less than 10. It's about 9.6 seconds. So it's going to take about 9.6 seconds for the ball to hit the ground. Well, now we've got a velocity function that can deal with that. And we'll know the velocity, or how fast the ball is traveling, when it hits the ground. So throw that number that we got, which is this square root here, into the velocity function, right? Velocity and at any time t is 9.8t, and so we're just going to take this number, multiply it by the 9.8, and get an approximate velocity of the ball as it hits the ground. And going to the calculator, we get about 9.94 meters per second. That's how fast it's traveling. That's pretty fast.